Okay. Thank you, Jenny, for the invitation, and thank you to the Biocurator Working Group for having me here. I'm so excited to be able to share with you about the matched annotation from the NCBI and EMBL-EBI, the Maine project. It's a new joint initiative together with the NCBI. And what I'd like to do this afternoon or morning or lunchtime, not sure, depending on where you are, a little bit about the background and rationale for this project, and then I'm going to talk mostly about Maine, and then if we have time, I will try to sneak in a sneak preview of a new tool that we're developing called TART. But to start us off, I don't think I need to convince this audience that understanding the impact of a variant is dependent upon understanding the gene structure and function. And obviously central to that is the accurate and comprehensive annotation of transcripts. Now, as you probably know, the more accurate and comprehensive the transcript annotation is, the larger the number of transcripts that will be defined at each locus. And that, combined with a lack of standards across the board in terms of reporting and browsers and so forth, that can present some challenges, especially in the clinical context. So the two groups who've had both the EMBL-EBI and the NCBI, we've had a long-standing collaboration as part of the CCDS project, which stands for the Consensus Coding Sequence Project. And so we'd already been thinking through what could be a possible solution for this particular concern. And so we started thinking through, should we define a joint representative or default or canonical, whichever phrase you want to use, should we do this jointly and would that be helpful? And we thought, well, it would be helpful in terms of standardizing the transcripts that you see in genomic browsers. So for example, VEP, Nomad, all of the resources that I've listed here, they each have their own default canonical, but they are not always the same. And so it can be challenging if you're trying to use all of these resources at the same time. You're constantly moving from one default to the next. Also, we thought if it's useful to find one canonical, then it should be a transcript that captures the most information about each protein coding gene. At the moment, if you look into what these canonicals are, sometimes they are the longest, sometimes they are the first one that was characterized or described, and we thought we could do something better in terms of finding a canonical that is representative of what's happening at that locus. We also thought it would be really useful for standardizing clinical reporting, and so we know that differences in annotation between the RefSeq set and the GenCode set, that makes it quite difficult to exchange data or to translate coordinates. And so we thought this might be really useful for clinical reporting. And finally, for those that's interested in comparative or evolutionary genomics, having a starting point, again, is really useful. So for all these reasons, we thought, well, maybe this is a good idea. Let's see what other people think. And here, I just want to say, an important caveat about this project is that we're not saying that we're defining a set for clinical interpretation. That's not what we're doing. We know that all transcripts at a locus are valid and useful and should be used. And we're also not saying that you can reduce biology to a single transcript. We know that that's not the reality of what's happening for many genes across the genome. This is more about standardizing and about bringing the community to be able to have a useful tool that they can use for all the reasons I've mentioned above. So the first thing that we decided to do was to try to get some community input, and I'm going to just walk you briefly through a survey. I know that many of you or some of you might have seen it. It came out about a year ago. And here we thought, well, if we're going to go ahead and do this, let's check in with the community to see their thoughts on the matter. And we had about 800 responses. When we looked at the people, how people had self-described, about 20% said that they were working in the clinical context or in the clinical community. And the questions that we asked The first one was, in the case of a gene without any known clinically relevant variants, which transcript should we make as the primary? And here we gave two choices. You can either go with the longest, that was choice A, or go with the most abundant, that's choice B. And what's interesting immediately was that there were differences of opinion. So the clinical people who self-define as members of the clinical community, they were about 50-50. You could go either way, abundant or longest. However, for the non-clinical community, abundance was a much more important factor. We then asked the second question, which was, in the case of a genes with clinically relevant variants, which transcript should be the primary default? And here we gave the choice of, again, the longest, the one that captures the most pathogenic variants, or the one that's the most abundant at the locus. And what the responses we got, again, were really interesting. Again, a separation between what the clinical community thinks, which is that it should be the one that covers the most pathogenic variants, whereas the non-clinical community gave about equal weight to the abundance versus the coverage of variants. And then we went ahead and asked the third question and final question. In a case of a gene with clinically relevant variants, which one should be the default? And here the choices were between the one that's the most abundant across the board in all tissues, or the one that's the most abundant in the particular tissue that is known to be related to disease. And again, here we saw a difference. The clinical community preferred, by and large, the transcript that has the abundance in the clinical tissue, whereas for the non-clinical, it was a toss-up between the most abundant overall or the one in the tissue. So obviously, these results were conflicting, but what we learned from it is that we cannot make everyone happy. So this project needed to be able to suit all the communities, but we knew in selecting one, it would be very difficult to pick a transcript that made everybody happy. And for the clinical community, especially, we understood we needed to take into account the coverage of clinical variants. We needed to take into account abundance, expression, conservation, looked at the tissue of interest. And so with all of this information, we went ahead with our main project. Now, before I move on to talk a little bit more about Maine, let me just give you some background about the transcripts themselves. So I think everybody in this group knows that there are two main sources of transcript annotation, the RefSeq set and the Ensemble GenCode set. The RefSeq is produced at the NCBI, whereas the GenCode set is produced here at EMBL-EBI. And the NCBI produces NMs, and those are manually annotated. They also produce XMs, which are produced in an automated manner. The NMs don't need to match the primary reference genome. They do represent a preference field, but it's not always the one that's on the reference. And this, I'm sure you are very aware that clinical annotation is predominantly done using these RefSeq transcripts. Now, the Ensemble GenCode set, those are the ENSTs, and they are more manually reviewed compared to the RefSeq set. They must match the primary reference genome. On average, they're more in-depth in terms of there are more Ensemble transcripts per gene compared to RefSeq. And increasingly, it's become the reference set for these larger scale projects such as NOMAD, GTEx, Decipher, and so forth. So for the clinical use, but broadly speaking, both sets are used. Both sets are comprehensive, they are complementary, but they are not identical. And that's an important point to know. So when we started doing this project, we knew that there would be differences, but we didn't know what we were going to find. So I've already said what Maine stands for, but the goal here was to produce a set that would have the following attributes. It must match GRCH38, and that's because GenCode must match 38. And it also must represent a pairing of a RefSeq and an ENST that are perfectly identical at the 5' UTR, at the CDS, and at the 3' UTR level. So these are transcripts that are basically identical and can be used synonymously. Also, these transcripts should be well supported, well expressed, well conserved, and representative of biology at each locus. Now, we are doing this project in 2 phases. We are currently in phase 1. This is where we are releasing what we're calling the Maine Select set, where we have 1 transcript for each protein coding gene. And the goal here is that for this one to be used as the default in all the browsers and all the resources. But we're also doing a second phase, and that one we're calling Maine Plus. And these are additional well-supported transcripts that are of particular interest. So for example, for clinical reporting, we know that there are some genes where only having that you cannot report all the variants using 1 transcript. So it's useful to have additional ones that are well-supported and are matched between the NCBI and the EBI. So let me say something about the methodology so you understand how we've gone about selecting our select. And the first point to make is that this is mostly an automated effort with a layer of manual review on top of it. And so the first step was for both groups to build independent pipelines to select a transcript from each set. Here I'm showing what each pipeline took into account. As you can quickly see that the 2 pipelines generally took into account similar kinds of information. What's interesting is that the weighting that it gave to each component is different. So for the RefSeq pipeline, expression and conservation fared quite high, whereas for Ensemble, the length was more predominant, and the Ensemble pipeline took coverage of pathogenic variants, whereas the RefSeq pipeline took into account prior manual curation, what the LRG project has done. And so the goal here in a more user-friendly display is you start out by having your 2 sets. You have the RefSeq set and the Ensemble GenCode set. You have your pipelines that then select 1 transcript at each locus. We then review and compare the pipeline results, and the review might help us realize that there are differences at the UTR level. We then end up in an effort to match and to make these transcripts identical, and they must be identical at the splicing, at the CDS, and at the UTR level. Again, to make it Maine, it must be matched and synonymous. So when we ran our pipelines, the first step was to compare the outputs, and we first found the hoped for and wanted bin. This is where the 2 pipelines had identical transcripts, and but we also found that there's a second bin where the pipelines had picked the same coding sequence, but these transcripts differed either in the UTR level, or in terms of length, or in terms of splicing pattern. And then we found a third bin, which is where the pipelines had picked completely different transcripts. You can see this example here where the pipelines had picked different CDSs. And so the first thing to note was that the hoped for bin 1 was actually the smallest bin. The second bin ended up being the largest bin, where the vast majority of cases were actually in this one here, where the only difference was in the UTR. But we found a good number of genes in the third bin where the differences were at the CDS level. And what we quickly realized was that this was a pool of very complex loci. And in fact, many of these genes represent or require annotation updates. So the reason the pipelines were not able to pick complementary transcripts is because the complete set differed between the RefSeq and the GenCode set. So for those, we will need to update the annotation fully. Because the largest bin was the second bin, we decided to focus our attention on that one. And our first point was to reduce, how do we reduce this bin? Again, this is the one where the CDSs match, but not the UTRs. And so the first point there was to define rules on how to define the extent of the UTRs. Now, I know that that may sound trivial, like you should be able to quickly match the UTR. However, this was actually quite a complicated task. And we ended up coming up with a concept of the longest strong, which I will describe in a minute. But once we managed to define the ends, then we trimmed or extended in an automated manner. I'm going to now illustrate what I mean by the longest strong with an example for the 5' end. Here is the KNG1 gene, and just to walk you through what you're seeing at the top the NM, in the middle is the ENST, or the ENSTs, in this case there's more than one, and here you can see the RNA-seq data for this gene, and importantly for the 5' end are the CAGE counts. And CAGE, for those of you who are not familiar, stands for CAP analysis of gene expression, and this is developed in Japan. And essentially, it's a way of quantifying the abundance of an RNA with a particular start site. So if you look here, you can see I'm showing you the highest peak. That means what we're calling the strongest, and that means that there's a large number of transcripts that start at this position on the genome, but you can see that there are other peaks. And so you could choose the strongest, but then if you do that, you can see that there's a large number of transcripts that are not included within that length of the UTR. So that length would not be representative of what's happening at that locus. But if you go for the longest, which would be the longest transcription start site, that, again, you can see by the RNA-seq data that would not be representative of what's happening at the locus. So after several algorithms and trial and error, we came up with what we're calling the K, because we went from A through K to pick one. We found what we call the longest strong, which is a point where there's a large number of transcription start sites that do start at that position, and it is more representative of what's happening at the locus. Similarly, for the 3' end, and I won't go into great detail, but here the key kind of metric is the poly-A-seq data. And again, you look at the longest, the strongest is not in this frame, but your longest strong is the one that captures a large number of ends, and it is more representative of what's happening at the locus. So once we were able to define this algorithm, we were able to significantly reduce that second bin where the differences were only in the UTR. But what about this third bin where the transcripts are totally different? What can we do about that? So the first thing we tried to do was to improve our pipeline. So we took a number of genes in this third bin, and we asked the question, what is the problem? Why are the pipelines picking different things? And what kind of data would we look at to reconcile the difference? And what we realized was we found data that we could use, and we did improve the pipelines, but frankly, the largest number of these genes, we couldn't, even improving the pipeline couldn't help us resolve the discrepancy. And that's because these are just very complicated genes. So this is by far the hardest bin. In some cases, there is just no right answer. You have more than one transcript. They're both valid in every metric, both relevant, both are of interest for any community. And so you have to pick one. And that is one of the issues with this project, is that by definition, you're selecting one. And these are the examples where selecting one becomes quite challenging, and it requires quite a bit of manual oversight. So this is biology, and that is that. But in other cases, what you have is a situation where a full annotation is required because the transcript corresponding the corresponding transcript in the other set basically does not exist. So this one in light green simply doesn't exist in the dark green set. So where are we now after reviewing and working now for several months on this project? We are at this point that by the end of September, we will have released a select transcript for about 67% of genes. We are calling this the Maine Select version 0.6, and this will be available by the end of September. In fact, I'm pretty sure by next week, they will be available on all the browsers and on the FTP site. We have also identified an additional 4%, which will be released via a dedicated track hub also at the same time as the 0.6 version is released on the browser. So our aim for the rest of the year is to increase that percentage to 75 to 80% coverage across the genome. And obviously our goal is to achieve genome-wide coverage by 2020. That is a very lofty goal, and we are working towards that, but we know very well that obviously the closer we get to genome-wide coverage, the more difficult it will be for this process to be completed. As I mentioned already, there are numerous very complex loci where the annotation will have to be updated and refined, and we know all of this will have to be done manually. So we know that this process, we've released quite a large number of transcripts, but we will have to slow down a bit. It will happen, but we are working towards that whole genome coverage by 2020. Now, one big focus of our effort is thinking about the clinical community. We know that, as I said, it would be great for the Select to be used as a default for clinical reporting and for other, for browsers and so forth. So where are we in terms of the clinical genes? What are we doing about the clinical genes? Well, we are working very closely with our clinical partners within the UK-based Transforming Genomic Medicine Initiative. It's the TGMI, and that's a UK-based consortium. But we're also consulting with collaborators in ClinGen, with Heidi Ream, and with other collaborators in the US. And the goal here, obviously, is to get a good sense, a good input and feedback about what we're producing and whether or not it's going to meet the needs of the clinical community. And in everything that we're doing, and everything that we do manually, and everything that we release, we are giving higher priority to genes that we know have a strong gene disease link. So we know they have been validated by the community and we know they are clinical genes. And when available, we take into account tissue specificity or the element that is the clinically relevant when making our decisions. So in those cases where we might be stuck between two really good transcripts, we would then take into account, is one more abundant in the tissue of interest? Is one more abundant or relevant in the stage of development that's important in the clinical context? And if that's the case, then we make that one the Select. Now, in terms of...
Yeah. Sorry to interrupt. I think one of our participants has a question. Missy, yes. Do you have a question?
Yeah, so I was just wondering, going back to, you've talked about all these different bins and then yes. The ones to release. I was just curious what the breakdown actually is across those bins. I'm assuming the majority falling in bin 1 or bin 2, but yes. Wasn't sure what that was. And then when you're selecting a transcript, if you're doing any validations or sort of QCs against pathogenic variants that are known to kind of make sure that, you know, those are being covered.
Yeah. So to answer your first question, so we've released 71% across the genome. What's left is about a 15% where the CDSs are different. there's about a 7, I don't have the slide in front of me right now, there's a 7% where the UTRs are different, but we think we can get through those either by manual curation or by looking at additional data. And then there's about a 7% where it is just going to be really difficult. And we had hoped that that final bin 3 or final percentage there would be much, much smaller. But we are at the point that, yeah, that there's at least 5 to 7% where it's just going to take a huge curation effort. And we're thinking through, and if this group has any brilliant ideas on how we could, if there's a way of releasing things in a particular order that would be helpful or with particular flags, but that is kind of where we are. In terms of your second point about QCing, so the pipeline that was produced by Ensemble does take into account all the pathogenic, likely pathogenic variants that are in the public domain. So it takes into account anything from ClinVar, it takes into account things that are in HGMD public, what's publicly available, and we also take into account variants that are in Decipher. So we are, in that way, taking into account variants, but one big goal for the project is that once we have a set that's fairly complete, that we will liaise with members of the community, such as your group or any other group, and do some QC at the level of, does this work? Can you use this? Or is it missing any transcript that you think is absolutely essential for the work that you're doing? So I hope that answers the question, but that's where we are.
Yes, thank you very much.
Sure. Okay, so I was just saying that basically the coverage for clinical genes is about similar to what's happening across the genome, and obviously it's an effort. So where can you access the existing Maine that have already been released? So I'm showing you, it's in all the browsers and it's on the FTP. I'm going to show you here what you can see in Ensemble, but also NCBI and UCSC. So in Ensemble, this is the usual view. If you search by gene, you'll be able to see a flag that is clearly the Maine Select flag. Now, as I said, we are, the release of version 6 or 0.6 is imminent, and that's the flag that you will see starting probably next week. And what it does is it shows you that flag, and it also shows you the matching NM. So if there is no NM on this in this column, then that means that these transcripts in here are not part of the main set. Eventually, we envision a flag for Maine Plus once we start working on phase 2. You can also see in this summary, you can see the RefSeq name here, and what basically this is flagging for this gene contains a transcript for which there's an identical RefSeq match. So that's a way of quickly in Ensemble seeing if your gene is in Maine. Similarly, with the NCBI browser, this is their genome data viewer, and you can see up here the RefSeq, then you can see the Ensemble set, but importantly, you can see that they are actually showing you the main release 0.6. And hopefully it's clear that these two transcripts are synonymous, they're identical, and you can use either identifier, and it's pretty much the same. And then if you look at UCSC browser, again, if this is your favorite browser, here is the main version 0.6. So, and finally, if you're interested in displaying the data as a whole, or if you're interested in getting just an output of all the genes, and if they have the main and the identifier, then you can go to the NCBI's FTP site and download all the data. And this particular one that I'm highlighting is the one where you would get just a spreadsheet with all the genes that are in Maine and the relevant identifiers. Now, I shouldn't move on from phase one without talking about the limitations, because obviously Maine Select is not built to capture the biological complexity at each locus. I mean, we are picking a transcript. It's a single choice. And so we know that for many, many, many loci, that's just not enough to capture what's actually happening at that locus in the cell. And also, it is very possible that by any metric, you are excluding transcripts that are just as good as the Maine Select. And we have seen examples of that, and that's probably what's in that third bin, where definitely it's a very tough choice sometimes in the Maine Select. Also, it's impossible to capture all the tissue specificity and patterns of expression when you are selecting one transcript. It is possible that the most highly supported transcript is just not the one that is in a particular tissue or is the one that's clinically relevant, because we're only choosing one. And finally, there are just gaps in data, and that 5%, 5 to 7% that I just mentioned, where it's going to be hard, it's because of this. This is something that we did not necessarily expect, but it's become clear that for some genes, we just don't have enough data that's pipelinable, or even that it's manually, that we can make good sense of. It's not available. We know that this will change. We know that there's additional data that's being produced, and maybe a few years from now, we might be able to make a better decision. But the Maine Select set is a snapshot of the data we have now. So what are we doing next? Well, our number one priority is getting to 100% for the Maine Select. We know that for a set to be adopted, for browsers, for pipelines, for all the clinical work, we need to have full coverage. And so we are actively working on that and thinking strategically about how to be efficient and increase our numbers. But also we're starting to think about Maine Plus. It's coming. This is the one, it's an extension of Select, but here we are finding additional transcripts of interest, and it's just like Select, it has to match 38, and it represents a pairing of a RefSeq and an ENSP that are perfectly matched at the UTR, at the CDS, and at the both UTRs and CDS. So this is a way of finding other transcripts that are required and useful in addition to the Select. Now, what are we doing for Plus? Well, at the moment, we're reviewing mostly clinical genes to try to assess how many have additional transcripts and figuring out ways that we can build to identify those additional transcripts. And we're aiming to start releasing something by next year. So that's a brief summary of Maine. I think I should just quickly show you this additional slide. I know that many of you are familiar, or some of you might be familiar with the LRG project that had the similar goal of identifying sequences for reporting and including transcripts. And it's the same group of people that work on both projects. And what we've tried to do, instead of duplicate, we are trying to synchronize. So what we're doing here is, for those of you familiar with the LRG, it's a record that shows you which transcripts are useful for reporting. And what we're doing is just now showing you the relationship between the Maine Select and what is already in the LRG. In a large number of cases, they are identical, as you can see here, but in some cases, they're not, and that's because the Maine has its own criteria. It's meant to be the way that we built it is with all the criteria that I mentioned at the beginning, whereas the LRG tended to more focus on including protein coding exons, regardless of whether or not they covered pathogenic variants or whether they were expressed or conserved. We very much envision that the LRG effort will diminish as the main effort increases, but for those of you who might be familiar or using LRGs, I wanted to communicate that we are now encouraging the community to use Maine. We do see a use case for LRG in the future where mostly for genes where the primary reference is broken, that still does exist. I'm giving you two good examples, ABO and SHANK3. The reference is broken. That means that GenCode cannot produce a transcript that is protein coding across that region. That means that by definition, we just cannot release a Maine select because Maine has to match the reference. So for those, we are going to create LRGs so that at least we can define a transcript, and it will likely just have the NM with no ENST because the ENST just cannot match a sequence that is different than what's on the reference. So no need to show this, but in summary, NCBI and EBI are working together to review our annotation and produce a matched set of high-value transcripts. These transcripts need to match 38, and they do represent a perfect match between the RefSeq and the ENST. The first phase of this is to define the Maine select to be a default, a canonical, and then we will start defining additional well-supported transcripts for the clinical and for any community, but for reporting or any particular use cases. And then I'm putting this here, Maine help at ebi.ac.uk. If anything that I've said is interesting, obviously you can email me. I think you'll have my information, but you can also contact us through the Maine help and just share some ideas that you might have or volunteer to do some testing for us. Yeah, and just to say that we do expect that all transcripts that are needed for clinical reporting, that is for reporting of known variants, pathogenic or likely pathogenic, that those would be represented in both Select and Plus. And so here are all the people that have done the work. It's quite a few people, both, but I just want to make sure you see that it's a joint effort by the NCBI and by us here at the EMBL-EBI. We have different funding sources that are shown here. But again, please contact us. I'm not sure I have time to go through TARG. Jenny, do I have 2 minutes to go through TARG, or should we just go through discussion and questions that people might have?
So I see, I think a couple of folks have questions.
Okay.
So maybe if we could have a few minutes for questions first,
yes.
And then move on.
Yeah, let's do that.
Great.
I can't
so
see
much.
the questions. If you can read them out loud, that would be helpful.
So I see that Matt Wright has a question. Matt, do you want to go ahead?
Hi, Joanella.
Hi.
Yes, I wanted to know that in addition to downloading the Maine Select transcripts via the FTP site, do you plan to make these available via the Ensemble REST API as well?
Yes, that is planned, and also in BioMart and some of the other tools. So yes, the plan is for full programmatic access to this.
Sorry, what was the timeline on that? Did you say like by March next year?
Well, I believe, so the Ensemble release is imminent, so I'm thinking next week the version 6 will be available. But I believe the version 5 is already available on the API. So, but I can't guarantee that. But I'm happy to look into that. But I know the intent is for it to be fully accessible.
That's great. I'll go take a look. Thanks.
Okay.
And then there was a question from Heike Torkler. Heike, are you there? Do you have a question? No, maybe not. And Missy, did you have another question?
No, I got them lumped in together. Thank you, though.
Oh, great. Thanks. And any other questions for Joanella before she moves on with the next part of the talk?
But I mean, if I could ask a question of the group,
Sure.
maybe it would be really helpful to know if what we're doing will be as helpful as we're hoping it will be for the clinical community. And are we going in your view on the right track? I mean, it's always useful to get feedback, and I have a group of people that can give me that. So if anybody wants to comment on that, that would be really helpful.
Any thoughts on that? Personally, I just feel like that the standardization is just always so helpful, so that, you know, anybody, whether it's clinical lab researcher, curator, you're looking at the same thing from whichever source you're taking it from. So standardization and consistency is, I think, always a good idea. I don't know if others have.
And I was going to agree with that, Jenny. I think the standardization is such a huge step. I think it's really going to be sort of on a gene by gene level. We're going to have to evaluate these to see how well the selected transcript is capturing everything we need from a clinical standpoint, or not. And hopefully it is, which would be ideal, and then working to address when it isn't. But it's a good, I mean, this has been needed, at least in my opinion, this has been needed for a very long time. So I'm glad people are working on this and heading, putting us in that direction. So thank you.
Sure.
Hi, this is Lemuel Rakacha. I just want to comment that this has been fantastic. I've been waiting for this for a long time. When do you think that any of the ClinGen expert panels will start utilizing this in some of their scoring algorithms?
Great question. Well, we are hoping to finalize it next year, but what I'm hearing from your collaborator who just spoke, I think this needs to be tested, right? And so I envision there being some sort of pre-implement. So we will release it, and it will be available for everybody. But I imagine that we are going to get some feedback that we could take into account. But we're hoping that by next year we would be able to release a full set. And that's actually a question I have for you. So how useful is it to, say, release 100% of clinical genes, but not 100% across the genome? Or is it useful to release 75% of genes across the genome? Do you see what I mean? So at the moment, we are aiming for 100% because we think that's the most useful. But can the community cope with, say, 75%? Or can they cope with 100% clinical, but 80% overall? Does that make sense what I'm asking?
Yeah, no, I could see that the challenge. I don't know if anyone else from ClinGen is online, but I'd like to hear their thoughts. My thoughts are, just sort of piecemeal is to look at what's already been curated or on the ClinGen expert, and then move from using that as a priority list and then going to the other expanded genes, I guess, being tested out.
Okay.
I think we had some other folks with questions too. Heike Torkler, did you have a question? And Dimitri?
Yes, so I'm just curious. If, let's say, in a year from now, we're going to have a Maine Select and Maine Select Plus, if we combine them together for purposes of mutation calling algorithm, would you think it would be sufficient and complete set?
Well, the goal would be that it would be for reporting, that anything you would need for reporting would be either the Maine Select for that gene, or it would be in Maine Plus, because at that particular gene, you need more than one transcript. That is what we're aiming for, and that would be the goal. But obviously, as I said, we have built our pipelines based on current. It's a snapshot of current data. So as more clinical genes are uncovered, or as more pathogenic variants are uncovered, I can imagine that the plus set is likely to grow, because if you have to report a variant and you can't do it with either one of the transcripts already in Maine, then you would have to grow Maine. So with that caveat, the goal here is to be able to represent all known variants that are out there.
And sort of unrelated directly to that, but I'm just curious, there are instances where there are some transcripts which only exist because of the genetic alteration, so they don't exist as wild type. But historically, they have been, for example, noticed in some of the cancer cell lines with mutation and have been listed as a transcripts, but they don't really exist without this mutation.
Yeah.
So I'm just wondering, do you have any efforts to try to at least label such transcripts?
So the one example that I'm familiar with is what we've often called a meta transcript, which is sort of it doesn't exist, but it has all the exons that are relevant in one model, one possible, and that's useful if you're reporting, if you're simply using it as a tool for reporting. But because they're not biologically real, you can't really use it for interpretation, let's put it that way. We know those transcripts exist, and in fact, in the context of the LRG, we've made a few, but the feedback we receive from the community that we've spoken to is that that's not the most useful. So we're not at the moment planning on doing that.
Right. I was actually going a little bit in the opposite direction, where essentially, if they exist, make people aware what this is artificial constructs. Because what happens is sometimes, for example, especially in tumor suppressor genes, there are transcripts which are listed, but there is no evidence they exist without this mutation. But what it causes a problem for algorithms which try to use them, for example, to try to figure out isoforms.
Okay. Well, I'm not very familiar with this. I mean, I would love to be in touch with you and talk about this more, because, I mean, if it's something that's useful, we can certainly consider it. I'm just not as familiar with the examples that you're bringing up. Is that all right? Can we be in touch?
Absolutely, yes. And again, it's a very, very limited number of cases, but I was just curious.
Sure.
Would you like me to facilitate exchanging email addresses?
Yeah, that would be great.
Okay.
Yeah, thank you.
Sure, thank you.
Thanks. And I think we have one more question from Shulin Zhang. Shulin? You might be on mute.
Yes, that was a terrific job. I think that's really needed, and because I came from clinical lab. And I think that from the clinical reporting point, at the moment, if we even do the whole exome, it's only about 6,000 genes that has some, clinical relevance, direct clinical relevance that's necessary to be reported. So in that way, if you can prioritize those like 6,000 genes, and no matter they are complicated or that will be great help for the clinical community. Okay. That's just my thought. But generally, it's a really terrific job, I think.
Great. That is another really useful way that your group can help. So I have been in touch with Heidi from ClinGen, and I've asked for some clinical genes. And I know that there are the working groups that are actively curating but I'm happy to collect clinical genes as if there's a consensus of the ones that are clinical, even if they haven't yet undergone your disease validity kind of curation, that I think would be really helpful.
Right, because I think that, from your first slide, you showed different opinions, and on the research basis, and the researchers always tend to find something really new and newly identified transcripts, but on daily clinical basis, that a uniformed use of a transcript is really helpful, so that we are on the same page, and leave this remaining to the researchers that they find a new transcript or some rare tissues in that way that you can add on in the future.
That's great. Great feedback. Thank you.
So are there any other questions? We have about 8 minutes left. And I know you had another few slides, Joanella. So.
Yeah, well, I'll just show you the first one to give you a sneak preview, and then maybe there might be another opportunity to show in more detail. But we're building this thing called TART. And I'll just, maybe I'll leave it at that, and let's just say what we're doing is it's meant to be an archive of all transcripts, past and present, from all sources. So that means RefSeq, Ensemble, LRG, from 37, from 38, 36, and all the past and present transcripts. And the idea is it's a tool to ensure full transparency about transcripts so that people can know how transcripts change over time. And it's also a tool to allow comparison of transcripts. So for example, you take an NM and an ENST and you want to know how they differ, or one from 37 to 38 and you want to know how they differ, this tool will be able to give you the answer, and it will always, you will always know any historical transcripts that have been used for clinical reports will always be available. So it's an archive, but it's an archive that has some added functionality such that you can find things and you can compare things. So I know, and the address for this is, here we go. It's this. So if anybody thinks that this would be really useful, here's the URL. It's still in beta form. It's under construction. We haven't released it, but this is it's good enough that you can go and try it and tell us what you think. And if anybody in your group wants to give that a try and think that this would be helpful, then you can contact me, and I would value some input on that.
Great. So any other questions?
Just quick question to this resource. I've never used it. It sounds very interesting. But for example, if somebody has a question, this transcript from RefSeq and this transcript from Ensemble identical, can this tool quickly give you an answer? Yes or not?
Yes. Yes.
Wonderful.
So if you can see it here, basically this is what it would look like. You search by gene, and it gives you all the transcripts from 8 and 37, and then you can select 2 transcripts here, or more. You can compare, and then it also shows you which one is the main select. But you can compare, and then it will tell you if they are the same and how they're different, if the difference is at the UTR or at the CDS level, for instance. And it's especially useful if you're comparing something from 37 to 38 and you want to know how the transcript has changed and whether anything at the CDS level, for instance, has changed. It can tell you that.
Wonderful. Thank you.
I see a message from a participant saying this is much needed and wonderful in capitals. So I think we all agree this is really fantastic work, and yeah, has generated a lot of excitement. So thank you so much for talking with us today.
Thank you for having me. It's been a pleasure.
So we have